Hello there. This little slideshow is about related rates. I know it's a new topic for a lot of you, but we're going to try to walk you through a couple problems, explain what it is, and have this as a video reference for you so that you can come back and watch it as many times as you need to. I have some notes scripted in front of me, but I am kind of doing this for the first time, so if you hear me mess up or if I stumble over my words, I apologize, but I'm just going to keep kind of rolling with it instead of stopping and recording and re-recording over and over again. So related rates. What is related rates? Let me move this out of my way. Related rates, this is from Wikipedia, but it does apply. In differential calculus, related rates problems involve finding a rate at which a quantity changes by relating that quantity to other quantities whose rates of change are known. So a rate of change is something that is changing to something that are known, or something that we don't know. The rate of change is usually with respect to time. Because science and engineering often relate quantities to each other, the methods of related rates have broad applications in these fields, and you'll see some of them over the course of the next couple of days. Because problems to which related rate method applies often have nested functions as well as differentiating different variables, solving these problems often requires application of the chain rule and implicit differentiation, so please recall that. That's a problem we're going to do in a moment, but I have a little animation I'm going to show you first. So, we have a 6-meter ladder is against a wall. If its bottom is being pulled or pushed at a constant rate of 1/2 meter per second, how fast is the ladder sliding when it reaches 5 meters, 3 meters, 1 meters up the wall? So again, we have a rate that we know, this 1/2 meters per second, and we're relating it to other rates, how the ladder is coming down the wall, etc. So let's see what this is. So you can see what is actually happening. Here's a graph of dy dt. Well, what is dy dt? Dy dt is how this is changing, how that is changing with respect to time. If you notice, what happens is once it hits the ground, see how fat picks up? It continues over with this other function and does that. So I'm going to hide that. Alright, I'm going to stop this and show that. So now what we're going to do is we're actually going to solve this problem. We're going to solve it back on the other one. So you have a y variable, we have x, and we have 6-meter ladder. So I'm going to draw that picture. Let's see if I can have a nice, I'm just going to use this. So this was labeled y, this was labeled x, and this was our 6-meter ladder. You can tell by looking at this that this is a right triangle. Now we're going to solve the problem. I might have to go back again and see. Okay, there's a 6-meter ladder. If its bottom is pushed or pulled, so that means this right here at 1/2 meter per second. So let's go back here. So that rate, how this is changing, how is x changing? X is changing, and the way we show that in calculus is dx dt, is 1/2 meter per second. Okay? So that's what we're looking, that's what we have, that's the rate that we know. So going back to this, how fast do you think the ladder is sliding right here when it's 5 meters, 3 meters, 1 meter up the wall? Well, we'll do 5 meters first. So when it's 5 meters up the wall, so that's what we're looking for. So what is the change there? What is dy dt? What is that? When y is equal to 5 meters. So we have some things we have to do. We're going to come back to this problem in just a minute because I want to teach you something. A little acronym that I learned called DREADS. D-R-E-D-S. DREADS. DREADS, the D in DREADS means diagram. We want to come up with a diagram, and if you saw in the problem that we just looked at, we had that triangle. Our R stands for rates. Labeling those rates. And if you notice, we had the dx dt and the dy dt, the one we knew and the one we were trying to find. E is equation, and that's where we are right now in our problem. We have to come up with an equation that relates these rates to one another, that is representative of these rates using this diagram. Let's go there first, and then we'll come back and finish our dreads here. Alright, so we have a right triangle. We have 3 sides on that right triangle. What could be the equation? What could be the relationship that we use? One thing is popping to mind, and that is the Pythagorean theorem. And we all know from our days in geometry, the Pythagorean theorem is a squared plus b squared equals c squared. Well, right now we're going to use this information here. So one of these things is constant, and two of them change. The ladder remains constant. It's not changing from being 6 meters. However, y, the distance along the wall, and x, the distance flying out from the floor, they do change. This changes as the ladder goes down. This changes as the ladder goes out. So what I'm going to put in there is I'm going to put x squared plus y squared. But I'm able to put, since this is a constant, it's the only reason why I can put it in at this point, 6 squared. So now I have my equation. So going back to dreads, what's our next thing? Anyone can guess? It's derivative. Yes, we have calculus. We're learning calculus. It's the derivative. And we're going to take the derivative of both sides. So diagram, rate, equation, whoops, I didn't mean to do that. Derivative, both sides. So let's go back. Sorry if I'm talking fast. You can slow it down, pause it. You can do anything with this video, which is kind of cool. So what's the derivative of this with respect to t? Remember, t. It's going to be 2x, don't forget our implicit differentiation, dx dt, plus 2y dy dt, again, implicit. We're taking the derivative with respect to t. Since it isn't a t and this isn't a t, we have to use implicit. And 6 squared is 36. The derivative of 36, well, we know the derivative of a constant is 0. So now we have our equation. We took our derivative. And what is our last part of dreads? Let's take a look. Took the derivative. Substitute. And there's two s's here. And solve. So we're going to substitute our specific information and then solve. Cool. So let's substitute. We need an x, we need a dx dt, we need a y, we need a dy dt. We know y. Y is 5. Remember that from here? So we know this is 5 at this moment that we're trying to find. We have 6, which we already took care of. Now we need to find x. We have dx dt. We are looking for dy dt. All right, so let's do it. How are we going to find x? That's it. Let's go back to this Pythagorean theorem and solve. Well, we know that this is 5 squared plus x squared equals 6 squared. Or 25 plus x squared equals 36. Subtract both sides from 25, or 25 from both sides. We get what? X squared equals 11. X is equal to the square root of 11. Alright, so it's not a pretty number, but it's a number nonetheless. So we have 2 times the square root of 11. dx dt is 1/2 plus 2 times y. We already said y is 5 here. So we have 5 in there. dy dt we're trying to look for, so we're going to leave that blank. That's our variable. That's the rate we're looking for. And then, we don't know what the square root of 11 is off the top of our head. I don't anyway. So I'm going to do some math here with a calculator, some arithmetic. 2 times the square root of 11 times 1/2 equals, to 3 decimal places, 3.317 plus 2 times 5 is 10. dy dt equals 0. So I'm going to subtract both sides by 3.37 and get 10 times dy dt equals negative 3.317. Divide both sides by 10 in order to get my dy dt. And I'm running out of space. And when I do that, we get negative 0.332 meters per second as the rate that this is coming down the wall. The fact that it's negative, does it make sense? It would make sense because it's going down the wall. So if we go back to our original problem, it says how fast? Oh, how fast? So when we do how fast, we know that we're looking for speed, correct? And if we're looking for speed, then what do we need to do? Take the absolute value of that. So the how fast, the dy dt that we're looking for, the how fast is 0.332 A little sloppy there. Let me erase that. 0.332 meters per second is that rate. Now that is only the case when y is 5. So if we were going to try it again when it's 3 meters or 1 meter, we have to see if our rate would actually remain the same. So why don't you take a moment and pause this, as I'm going to pause it because someone just walked in, and try it, the exact same problem, but this time we are going to now use, so I'll just put a new slide in. Alright, so we're going to have the same triangle, same idea, 6 meters ladder. We have x and we have y. Our dx dt hasn't changed. It's still 1/2 meter per second. But this time our dy we're going to find it when y is equal to 3. So pause it here and try it.